Hi, I'm Suzette for ALGOR. Today's show, Solving the Case of the Impact Force, is number 2 in ALGOR's Escape from the Past video series. A typical problem for the ancient Greeks was determining whether a stone beam, such as this one in the Parthenon, would hold up once the scaffolding was removed. Archimedes and others worked out formula to determine the size of stone beams for specified distances between columns, dimensions for scaffolding, and the structural members of the hoist they used to lift these giant stone beams into place. Roman engineers elaborated on this work, but the equations were lost during the Middle Ages. By the 19th century, engineering had advanced to the point where the success or failure of steel beams in modern structures could be predetermined. The technique was to calculate a value known as stress, which is nothing more than a force spread over an area, and then compare that value with the upper stress limit for the iron, which would be determined by stretching samples in a laboratory. First, the engineer would calculate a quantity known as the moment of inertia based on the cross-section geometry of the beam. The next step would be to calculate the stress using formula like this. By the late 20th century, a technique known as linear static, finite element stress analysis had been developed which enabled engineers to do similar calculations on real parts such as engine blocks, suspension springs, computer fans, and so on. An engineer would pull a model from a CAD solid modeling system into the finite element system, apply static loads, and get the stress results. All of this would be fine except for one thing. Typically, unless expensive experiments are done on laboratory prototypes, the loads are not well known. Also, in an assembly of parts, each part would have to be analyzed separately, with forces being transferred cumbersomely and inaccurately from one part to another. In today's example, we will consider the case of this simple steel bar. We are placing it on these stands. So that it becomes a simple beam with simple supports at each end. We will now propose to drop a 4-pound weight on this bar from a height of 1 inch. This example, though seemingly straightforward, will reflect the same principle as a child slamming into the retaining bar of a child seat, a car slamming into a foam pole, gears clashing together when a motor is turned on, or the impact when rail cars couple. So according to the handbook, the maximum stress on this beam will occur here, at the point where the force will be applied. Let's try the calculation as follows. The stress is equal to mc over I. M equals the torque applied, which is force times distance. C equals the distance from the center of the bar to the outer radius. And I equals the moment of inertia. Okay, for this bar, I equals 0.003068. And C equals the radius 1/4 inch. And M for this case equals the force times the length, or 23 inches divided by 4, or force times 5.75. Now let's do the force. The force would be 4 pounds if the weight were not moving. We are going to drop it from just 1 inch. Now we don't seem to know the force. Wait, let's use Hooke's law. Force is equal to the stiffness of the beam multiplied by the deflection. Okay, from the same handbook, we get this equation. The deflection equals the force multiplied by the length cubed and divided by 48 times the moment of inertia and Young's modulus. And solving for the force, we get F equals 48 EI over L cubed times the deflection. Now, the bar is made of steel, so Young's modulus is about 30 million. So the force equals 363.1 times the deflection. Uh-oh, now we don't know the deflection. Oh, maybe finite element analysis will work. First, we build the model. Now, the boundary conditions. The material properties. And finally, the force. Wait a minute. We still need the force. What if we balance the potential energy of the weight against the energy stored in the deflected shape? We might get into the ballpark that way, but we still need to consider the inertia of the bar as well as its change in potential energy. Anyhow, that's just not practical for things in general. The only thing left to try is a virtual experiment using ALGOR's AccuPack VE. We already have the finite element model. Now let's add in a second model for the weight, precisely 1 inch above the bar. And let's be sure gravity is right. Now we can start the model running. The monitor program is plotting the deflection versus time as we go. And we can see the step-by-step analysis happening here. At the end, we can make a replay of the motion, impact, and stress analysis in an AVI format and look at it with the Windows Media Player. Right here is the maximum stress in pounds per square inch. And here is the maximum deflection. Now, just for info, we can calculate the actual force. Plugging in the deflection, we get the force. See? The force is 56.6 pounds. Wow, that seems high. Let's check this out with an experiment. First, I'll use this ruler to check the 1 inch height. This piece of cardboard will serve as our telltale maximum deflection indicator. Now we'll release the weight. Let's see. We have about 0.16 inches deflection. About the same as the AccuPack VE event simulation run. So far, so good. Now, let's get the force. For that, we will reverse the experiment. May I have a volunteer from the audience? We will use the winch to pull up on the bar until the deflection is about the same. If we insert the scale in line between the cable and the bar, it will read the same force that it took to bend the bar when the weight dropped on it. Okay, in the bar. Okay, go ahead and take it up. We need to bend the bar 0.156 inches, which is between 1/8 and 3/16 of an inch. Okay, Jackie, let her crank. A little bit more? Good. Let's see what we have. The scale reads 56 pounds. Here's another question. Suppose the expected real-life design calls for a weight of only 1 pound dropping from 1 inch. What is the safety factor if we have designed using the 4-pound weight in our experiment? Some think that the safety factor would be 4, that the force would be 56.6 divided by 4, or 14.15 pounds. Let's rerun the virtual experiment with 1 pound instead of 4. Now the process is taking place. And the deflection is 0.0634. Plugging this into the equation for force, we get about 23 pounds. So the safety factor is only 2.46. Suppose the anticipated operating force is equivalent to dropping the 4-pound weight from 1 inch, just as we have done today. And we want to design in a safety factor of at least 4. From what height should we drop the weight and check the stresses? Let's do this case on the computer. We need to get a drop height such that the force is 4 times 56.6, or 226.4 pounds. Now let's raise the virtual 4-pound weight to 19 inches. And plugging in the deflection to get the force, 228.69 pounds, that's close enough. We need to drop the weight from 19 inches to get a safety factor of 4. AccuPack VE Mechanical Event Simulation for virtual prototyping from ALGOR. It's how engineering will be done in the 21st century.
Yeah, that's so good. Yeah.
There, thank you for holding that spine. I don't think they can.
One little chirping. Chirp this flow. Okay. Roll camera.
Roll cameras on.
And action.
Hi, I'm Suzette for ALGOR Incorporated. Today's episode is titled Escape from the Past, or Solving the Case of the Buckled Bar. Engineering began in the ancient world. Among the many creations of ancient engineering are 3 huge pyramids at Giza, Egypt, known as the 7th wonder of the ancient world. Their method of construction is today shrouded in mystery. Engineering methods advanced rapidly through the millennium. Culminating with today's method of computerized finite element stress analysis.